couple others that I think would be pertinent as well. All right, Chemistry 3101. We're in Chapter 11. I thought we'd take a look at a couple of practice problems before we wrap up our class today. So here we're taking this alkene, and we want to end up with this functional group here. Could anybody identify this functional group? And it's not a trick question. Yeah, it's a carboxylic acid. Okay, so if you're wondering why didn't you draw it, why didn't you draw it like this? I don't know. It's just the way it's drawn as a condensed structure. So you can draw it like this if you want, or you can draw the condensed form. But you can see clearly that there is a change in the carbon skeleton. Here we're going from 5 carbons to a total of 4 carbons. So if I want to make a carboxylic acid, we could do a great retrosynthetic analysis here and say, well, if I had $1 million, no, if I had this alkyne, then I could just do an oxidative cleavage here, and that would give me the carboxylic acid on this side. And from this side, I would end up with CO2, right? Carbon dioxide. And so that would be the approach that we want to take here, right? So we're going to end up with this, plus we're going to end up with CO2, but we're not really worried about carbon dioxide in organic chemistry class. All right, so how are we going to get from here to here? Well, that greatly simplifies the problem now, because we know we can do an addition of bromine using bromine, of course. And yeah, we just need bromine. You could put a solvent like dichloromethane if you want, but let's put bromine, and that is going to do the dibromination. So we're going to have one bromine here and another bromine there, and then we can do our double elimination. So we're going to treat this with excess sodium amide followed by treatment with water, and that is going to give us the alkyne that we're looking for. So this compound has a total of 5 carbons in it. And then when we do the oxidative cleavage, so step 1 is going to be ozone, and step 2 is going to be H2O. There you go. That gives us the carboxylic acid that we want. Give me a thumbs up if you're with me on that one. Pretty good on that one. And again, stop me if you have a question along the way. Okay, so let's move on. Let's clean the slate here, and let's look at another problem that's kind of in a similar vein, I guess. This one, we're going to start with a primary alkyl halide. We're going to start with this compound, which has a total of 4 carbons. And then we're going to make this carboxylic acid here, where we have a total of 1, 2, 3, 4, 5 carbons. Now we know that if we're adding carbons, we can only add 2 carbons at a time, right? We can't add 1. Well, I guess we can add 1 if we're using methyl iodide as our electrophile. But here you would think of this as being our electrophile, right? This would be our electrophile. And so if we do a retrosynthetic analysis, it's kind of in the same vein as the last one, right? If we had this compound, it's not the prettiest little bond there, is it? Oops, that's even worse. If we had this alkyne, there we go. It's a little bit better, right? You see that our starting material has a total of 4 carbons. Our product is a total of 5 carbons, but this compound has a total of 6 carbons. And so if we did an ozonolysis, that would cleave off this carbon here and leave it as CO2 again. And again, we're not really interested in CO2 as organic chemistry students. And so if we want to make that alkyne, what are we going to do? We're going to take this and we're going to treat it with sodium acetylide, which will do our SN2, and that is going to give us the alkyne, the terminal alkyne. That is horrible looking. The terminal alkyne, which looks something like that, okay? And then in the last step, we're just going to do the ozonolysis. We're going to treat it with ozone, and then the second step, we're going to treat it with water like that. I thought these were both pretty interesting reactions. All right, let's continue on in this ozonolysis vein and take a look at another problem that involves that same process. So what if we wanted to take that same starting material, the primary alkyl halide, and we wanted to make an aldehyde from it, right? We want to add 1 carbon more. We want to have an aldehyde. Well, again, we're going to use ozonolysis to do it, but now instead of having an alkyne, we would want to have an alkene like this. And we know that if we do ozonolysis on that, that would give us an aldehyde plus formaldehyde, right? You'd also end up with with this compound, which is neither here nor there. We're not really worried about that compound. We just want to know how to make the compound that's shown here. So we're starting it with something that's got 4 carbons. Our final product has 5 carbons, and this intermediate has 1, 2, 3, 4, 5, 6 carbons. So we're going to use the exact same strategy we did before, where we're going to treat the primary alkyl halide with sodium acetylide. You can see I write it in many different forms. And anyhow, so we end up with the terminal alkyne, and if we want to reduce that to the alkene, the only way we can do that is hydrogen in Lindlar's catalyst, right? Note, for this reaction of a terminal alkyne, sodium metal reduction will not work. It's a very specific case. For a terminal alkyne, sodium metal reduction doesn't work. So that gives us our alkene that we want, like this, and now we can just do an ozonolysis. So we do ozone followed by treatment with DMS, and there you go, we get our aldehyde. Next problem I wanted to look at is this one here. So you can call this compound 2-methylpropane, or you can call it isobutane. Right? It's got the same molecular formula as butane. If we wanted to take isobutane and convert it into this alkene, okay? Well, we know that we could make this alkene from this primary alkyl halide, and if we treated that with sodium acetylide, and then we reduced it to the alkene, right? Reduce the alkyne to the alkene. So then the question becomes, well, how do I get from here to here? Right? How do I go from an alkane to this primary alkyl halide? Because if I treat isobutane with bromine and light, I end up with a tertiary alkyl halide. So I end up with this compound. But we know that if we treat this with a hindered base, like potassium T-butoxide, we're going to end up with isobutylene, this compound, and then we can do an anti-Markovnikov addition of HBr, and that will give us the primary alkyl halide, like this. After that, we can treat it with sodium amide, or sodium acetylide, rather, like this, and that will give us the alkyne, and then to reduce it, we're going to use hydrogen gas in Lindlar's catalyst. All right, let's try another one where we start with isobutylene as our starting material, and we want to make a methyl ketone. Right? How do we make a methyl ketone? Well, if I could make the alkyne, if I could make this alkyne, so 1, 2, 3, so 1, 2, 3, then I could just do a Markovnikov addition of water to give me an enol, and that's going to tautomerize to give me the methyl ketone. So then the question becomes, well, how do I get from isobutylene to the compound in blue? Well, hopefully you can see that the first thing you'd want to do is an anti-Markovnikov addition of HBr, which will give me the primary alkyl halide. And then I can do an SN2 with my sodium acetylide, which will give me the compound in blue. Give me the compound in blue, something like that. And then I'm going to do a Markovnikov addition of water across that triple bond. So for that, I need sulfuric acid, water, and I also need mercury 2 sulfate. And that is going to give me this compound, which is the enol. But remember, the enol is going to undergo tautomerization to give me the methyl ketone.